Gibson here. Today we're going to look at the first lesson as we begin to study motion in physics. The unit will be linear and projectile motion. Linear meaning in a straight line, one dimension, and projectile where we have motion in two dimensions, such as if we were to throw a ball up into the air at an angle. So for today, what we're going to do is understand the distinctions between things like distance and displacement and speed versus velocity. So let's take a look at our objectives for today. The first is, as we begin to study motion, understand that all motion is relative, but what does that really mean? Okay. Second, we're going to talk about the difference between scalar and vector quantities, and then look at examples of both scalar and vector quantities by distinguishing the difference between distance and displacement and speed and velocity. All right, so what do we mean by this concept that all motion is relative? Well, how would you describe this bike's motion? Well, you might be able to say it's moving left or right. But other than that, we don't have enough information to describe, for example, the rate at which it's moving, right? Its speed. And partly because it's just traveling across a blank screen. So we have no reference frame in which to describe its motion, particularly from a quantitative standpoint. Now, what if I put this background in place? Could you do a better job of describing its motion? Could you maybe make an estimate of the bike's speed now that you see objects in the background that are familiar to you, right? You know how big a path is along the beach or the size of a coconut tree that might be growing on the beach. Let's look at another example. We have a stack of books here on the table. Are the books moving? Well, I think most people would say no, they're sitting still on the table. But what if I put that table in a view that shows it sitting on the surface of the Earth? And we all know, right, that the Earth is rotating. So now, how would you answer that question? Are the books moving? Well, you might say it depends, right? It depends on the point of view of the observer that's looking at the books. So if you're standing on the surface of the Earth along with the table, you would probably say no, the table and the books are at rest. If you're off the surface of the Earth, looking at that stack of books, say from outer space, you would clearly say no, the books are moving along with the entire Earth. So the key point here is when we begin to describe motion, we need to keep in mind that all motion is relative to a reference frame or the point of view from which you're observing that motion. So the point of view where the books are not moving would be a reference frame that would be the surface of the Earth. The point of view where the books are moving would be a reference frame that is off the surface of the Earth, right? So we can see not just the book and table motion, but that of the entire Earth. Now, for most of the motion problems that we will begin to study here, unless we note otherwise, when we discuss the motion of things in our environment, we'll measure motion with respect to the surface of the Earth, okay? That we're standing on the surface of the Earth and watching objects move relative to the surface of the Earth. All right, key concept there. And this will show up a few times as we work through our content here for the rest of the year. Now, another important distinction we want to make before we get into discussion of motion is that we have two different types of quantities that we'll be working with in physics. The first is what we call scalar quantities. So scalar quantities are described by magnitude or a numerical value alone. Vector quantities are those that are described by both a magnitude and a direction. Now, as I begin to go through these lessons, you'll see key vocabulary, key formulas that are in this blue square here. So these would be important things to capture in your notes. So let's look at some examples and see if we can decide, are these measures that are scalar quantities or vector quantities? So let's just start out. Let's say 5 meters, right? That would be a way to describe the length of something. So would that be a scalar or a vector quantity? Well, it only contains the magnitude of the length, 5 meters. There's no information about direction. So we would have to say that is a scalar quantity. How about 30, let's see, this is a typo, I should have 30 meters per second, but east. Okay, now we have a direction. So this would be a vector quantity. How about 5 miles north, right? If we were to hike or drive 5 miles in a northerly direction, we have described a vector quantity. How about temperature, 20 degrees C? Well, we normally don't associate a direction with temperature. We might talk about its rate of change. Is it increasing or decreasing? But the magnitude itself does not have a direction. So we would say 20 degrees C would be a scalar quantity. Or something like energy, right? 2,000 calories. Again, we might describe a rate of change, but the magnitude itself has no information about direction. We don't really associate direction, right, with something like thermal energy. So that would be a scalar quantity as well. Okay, so as we go through this unit on physics and talk about motion, there'll be a number of different measures, and we will take the time to clarify, right? Is this a scalar quantity or is this a vector quantity? Very important distinction. All right, so let's see how that applies to distance and displacement, okay? So distance is probably the everyday term in language that we use. And that would be a scalar quantity, because in the physics context, it simply refers to how much ground or how far the object has traveled during its motion. Okay? It has no direction to it. The default unit is meters. And in terms of the variable that we're going to use to represent distance, we're going to use the small d for distance. Now, displacement is where we make a distinction. It's a vector quantity that refers to the object's overall change in position. So in order for us to determine the change in an object's position, we have to determine not just what distance that it traveled, but also what direction it traveled. Okay, so displacement has really the distance component to it, but also adding direction. And it's all about how far did the overall object change its position. The units are still meters, but the variable we're going to use for displacement is the small x. Okay, so if you see a small d, we're talking about distance. If you see a small x, we're talking about the object's displacement. So let's just summarize here some of the key differences. Distance, the amount of ground that is covered, a scalar quantity. Displacement is the overall change in position, a vector quantity. Let's look at an example here. We have a track, and we got a track star here who's going to take 1 lap around the track. And let's say this is a 400-meter track. So the question is, what distance did the runner cover, and what is the runner's displacement? Well, most people would say, well, you took 1 lap around the track. We know that the distance all the way around the track is 400 meters. So that would be how far our runner traveled, right? Have a distance of 400 meters. But what would his displacement be? Well, remember, it's the overall change in position. So where did he start and where did he finish? Now, clearly, If he took just one complete lap, he's going to finish right back where he started. So in this case, even though he traveled a distance of 400 meters, his displacement is 0, right? He's in the same position that he was at the start. Doesn't matter what path he took in between. Where did he start and where did he finish? Here's another example, right? We've got two paths here. Path A, you can see the start and the end points and the path that we took. Path B, same start and end points, but a different path that we took, right? So how would their distances compare? Well, I think clearly you would see that path A traveled a greater distance, right? This path is much longer, a curved path that zigzags, than the straight path in B. How do their displacements compare? Well, they both started and ended their motion at the same points. So they would have exactly the same amount of displacement. Okay, so for displacement, we don't care what path they took. Again, it's just simply where did they start and where did they finish and what's the difference between those locations. Now, let's go and define speed, okay? We understand what distance and displacement is, but how is speed related to, for example, distance, okay? So if we go back to our bike rider on the beach, and we were to take a camera where we could snap a picture every second of that bike rider's location. So that's what this clock represents, right? Our first time frame, and then the second time frame is a second later, 2 seconds later, 3 seconds later. We could replace our bike rider with just dots. It's a little bit easier to represent, right, than to have to draw the bicycle each time. But now, if we can add a scale that shows how much distance the bike traveled at each of those time intervals, we now have all the information we need to define the speed of the bike rider, okay? So if you ask people, so how fast do you think the bike rider is moving? You could say, well, he moved 5 meters in 1 second. He did that in the first interval. He did the same thing in the second interval. 5 to 10 is another 5 meters in another 1 second, okay? So we are able to determine his speed here based on the distance that he traveled and the time that it took to travel. So the way we're going to define speed is the rate at which distance is being covered. Rate meaning how much time. And from this example, we can clearly see that it had what appears to be a constant speed of 5 meters per second across these 3 time intervals. So let's officially define speed. Speed is the distance traveled per unit of time. Now notice I'm using the word distance, not displacement. For speed, all we care about is the total distance traveled and how much time it took to do that. So these are some common units of speed that we work with every day. Miles per hour, certainly when we're driving in a car. Kilometers per hour, if perhaps you're in Europe or parts of Asia, or really most of the rest of the world. But here's some other ways we might measure speed: centimeters per day, light years per century, right? Meters per second. Notice all of these have a measure of length or distance divided by a measure of time. Meters per second is the one that we will use as kind of our default unit of measure for speed in physics. So let's look at another example. If you look down at the speedometer of a car as you're driving, what is it really telling us? Is this the instantaneous speed that we're driving, or is it the average speed? Well, since we're looking at it at just a moment in time, it's the speed that we're doing at that instant. So the speedometer of a car gives us instantaneous speed. Okay, so we can define that as the speed at any point or instance in time. Contrast that to average speed, where the average speed is the total distance traveled divided by the change in time, or the total time that it took us to do that. So here's what that would look like mathematically. Now we're going to use small s for speed, and the little bar across it just simply means average. Okay, so if we're calculating the average speed, we're going to find the change in the distance. Now let me get my pen here a little bit. This might be the first time you've seen this notation where we put this triangle in front of the D. Okay, the triangle is actually the Greek letter for delta, okay, or D. So when we see that triangle, the delta means the change, okay? So the change in the distance divided by the change in the time. So here's a note that tells us what that symbol means. So we'll see this a lot as we work through this unit and this concept of change, the rate of change of a particular value. I already talked about this. The bar over the S means average. Okay. Now, this is what we sometimes call the speed equation or the rate equation. It has speed, distance, and time in it. And it's very useful because we can solve for any one of these parameters, speed, distance, or time, if we know the other two. So often we'll do problems where we have to rearrange this, right? And this is what other forms of it look like. If we want to solve for time, right, we would just switch time and speed, so we get change in distance over average speed. If we wanted to solve for the distance, it's simply speed times the time. Okay, so make sure you get this in your notes, the equation for average speed and the other two forms of it, depending on what we're trying to solve for, whether it's time or distance. All right, let's look at a couple problems here where you can practice this. Speedometer in every car also has an odometer that reads the distance traveled. So if the odometer reads 0 at the beginning of a trip and 35 kilometers a half hour later, what is the average speed that we've been traveling? Well, let's start with our equation. Right? Average speed is equal to change in distance over the change in time. What was our change in distance? Well, we went from 0 to 35 kilometers. And how much time did it take us to do that? It says half an hour. So we can put in those values, 35 kilometers. Now we want our answer to be in kilometers per hour. So half hour, we want to put it in the units of hours, so 0.5 hours. If I said kilometers per minute, right, we would put 30 minutes in here. So we got to pay attention to what units we're looking for in our answer. So the math is simple, right? 35 divided by 0.5 gives us 70 kilometers per hour. So that would be our average speed over that half hour. Now here's another question to think about. Would it be possible to attain this average speed and yet never exceed a reading of 70 kilometers per hour on the speedometer? So our instantaneous speed would never be above 70 kilometers per hour. Do you think it would still be possible to average 70 kilometers per hour? Well, the answer would be no, particularly if we assume that the trip started from rest, right, and it ended at rest, meaning at the beginning of our time period, right, the speed, the instantaneous speed, was 0. So there's no way we could average 70 kilometers if at any point during that trip our speed was 0 or even any value below 70 kilometers per hour. Right, let's look at a couple more examples, see if you can solve these, and then pause the video while you work on it, and then we'll put the answer up. The cheetah can maintain a constant speed of 25 meters per second. What distance will it cover each second? Well, at this rate, how far will it travel in 10 seconds? How about how far will it travel in 1 minute? So 3 parts to this question. What distance does it cover each second? So that's speed, right? Distance per unit of time. And then how far? That's our distance. So the first is quite simple, right? If it can maintain an average constant speed of 25 meters per second, that means by definition, it's going to cover a distance of 25 meters each second. So how far would travel in 10 seconds? Well, we rearrange our rate equation, right, to solve for distance. So distance is equal to our speed times the time. So we know our speed is 25 meters per second, times 10 would give us 250 meters. Notice I'm using our unit analysis method here to cancel out the units, so we can see that indeed our final answer should be in meters. How about for 1 minute? Well, because our speed is in meters per second, we need to convert 1 minute into units of seconds. So let's use a conversion factor, right? We know there are 60 seconds in a minute. The minutes will cancel out, and that now leaves us with 25 times 60, or 1,500 meters for our total distance. All right, so a couple of simple examples there of how we could use this rate equation to find average speed or distance. I didn't show an example where we solve for time, but that would be pretty straightforward. All right, let's try one more, a little bit trickier here. Let's say we have a driver who for the first 2 hours averages 25 kilometers per hour. And then for the next 4 hours, so here's our times here, she averages 40 kilometers per hour. So we want to know what is her average speed over the total time, right? So the 2 hours plus the 4 hours. So we start with our rate equation here, change in distance over change in time. We're not given distance directly, but could we figure out what the distance was in the first 2 hours? Well, yes. It's simply that the rate, 25 kilometers per hour, times the time gives us the distance, right? So we could figure out the distance she travels during those first 2 hours and the distance she travels in the last 4 hours. So here's what it would look like. 25 times 2 plus 40 times 4, and then the total time would be 2 plus 4, or 6. So if we do the math, we get 210 divided by 6, or an average speed of 35 kilometers per hour. Okay, notice this is not just simply the average of 25 and 40, because she traveled at those two rates for different time periods. If she traveled 25 and 40 for the same amount of time, then yes, the answer would be simply the average of those two. All right, so we understand speed, how to calculate it, but what is this thing called velocity? And this is really the key term for describing motion that we'll be using in physics. Well, velocity will be more important than simply the object's speed. So we've already defined, right? Speed is the change in distance per unit of time. Velocity, well, let me finish up with speed. Here's an example, 50 kilometers per hour. So speed is a scalar quantity. It has only magnitude. Velocity, we're going to define as the change in displacement per unit of time. So an example would be 50 kilometers per hour, but notice displacement now includes a direction, okay? So velocity is a vector quantity, has both magnitude and direction. All right, so here's a little thought question. The speedometer of a car moving east reads 60 kilometers per hour. It passes another car that travels westward at 60 kilometers per hour. So here we go. Here's our two cars, same speed, but traveling in opposite directions. So I just kind of answered the first question. Do they both have the same speed? Yes, they do, right? Because we don't care about direction when we're talking speed. Do they have the same velocity? Well, they have the same speed, but they do not have the same direction. Therefore, we can't say that they have the same velocity. Their velocities are different because of that direction. All right, so let's officially define velocity here. It's the change in displacement per unit of time. The units are still meters per second, but it's going to also include a direction. Remember, velocity is a vector quantity. And here's how we're going to calculate it. Now, we're going to use v, small v for velocity. Again, the bar over the top means average. And now instead of change in d or distance, we have change in x, displacement, divided by the change in time. Or another way to actually calculate this is to define the change in the displacement as the difference between our final position and our initial position. Let's blow up this equation a little more here, right? So the subscript f indicates the final position or the final value of x. The subscript I stands for the initial position or value of our displacement x. Same thing for time, right? We have our final time at the end of our travel and our initial time that we started. Now, many of the problems we're going to do, we'll just assume the initial time is 0, right? So subtracting 0 really doesn't change anything. We can just use our final time as the total change in time, okay? But final position minus initial position gives us our change in displacement, and then divide that by the total time. So let's go back to our track example here, right? We're going to let him run another lap, forwards and backwards. And let's say it took him 5 seconds. He's extremely fast, okay? What was the runner's average speed? Well, we know average speed is just simply distance over time, but then I'm going to ask you, what is the runner's average velocity? So distance over time would simply be the 400 meters once around the track divided by 5 seconds, or 80 meters per second, probably the fastest human on Earth. What is his average velocity? Well, remember, it's the change in displacement, and we already said that his displacement is 0. So no matter how slow or fast he runs it in terms of time it took him to do it, the velocity will still be 0 because the displacement was 0. He wound up exactly in the same place where he started. Okay. All right, let's look at another example here where we get a little more complicated with this concept of displacement and velocity, distance and speed. It says a deer walks 1,300 meters east to a creek for a drink. The deer then walks 500 meters west to the berry patch for dinner before running 300 meters east when startled by a mountain lion. The total trip took 10 minutes. So we want to find our average speed and the average velocity of the deer, right? So let's diagram this out, right? All these words make it a little difficult here, right? Because we really have 3 different motions, right? 1,300 meters to the east, 500 meters to the west, and then another 300 meters to the east. So it helps to kind of draw this out. So here's our starting point. The first thing we did is we went to the east, which is to the right, 1,300 meters. Really, I'm using a vector here, right, to represent the distance and the direction that we traveled. So this is really a displacement vector. Then we went 500 to the west. So we're using this concept of tail to head of the arrow, right, to add these vectors together graphically. And then the last is we went 300 meters back to the east, okay? So we'll show it this way. All right, so let's see. Let's calculate our average speed. So again, we want total distance divided by total time. Well, what's the total distance that we traveled? The distance is just simply the sum of all of these, 1,300 plus 500 plus 300. Since it's distance, we don't care about the direction. We just want the total path or ground covered. So if we add those up, we get 2,100 meters. Now it took 10 minutes to travel, but we want to have our time in the units of seconds, right? Because I'm asking for our units to be in meters per second here. So we would multiply 10 by 60. That gives us 600 seconds. So now we can find our final answer. The deer would have an average speed of 3.5 meters per second. Okay, so that's the first part. How about B? How about average velocity? Well, let's clear this off and start now with velocity, right? So velocity, remember, is the change in displacement. So that's our key question, right? How much is the deer's change in displacement? Where did he start and where did he end? And how much distance did he travel between the start point and the end point? Okay, so if we were to say, okay, here's our starting point, here's our end point, right? How long is this movement, this displacement from start to end? Well, we kind of can use these vectors again, but now we have to add them, taking into account their direction. So 300 meters to the east, let's treat that as positive. 500 to the west, we'll treat that in the opposite direction, or negative, so we'll subtract 500. And then 300 meters to the east again is positive. So 1300 minus 500 plus 300 will give us the length of this resultant displacement vector. So if we add all those up, we get 1100 meters to the east. Okay, so that's what we're going to use for our displacement. We still need to convert the time to seconds. So we get now an average speed of 1.83 meters per second. I'm sorry, average velocity of 1.83 meters per second, significantly slower, right, than what the average speed was, because it has less displacement than what the total distance was. All right, one more problem here and then we'll wrap this up. So Scat, the angry squirrel, travels 4 meters east and 3 meters north in search of an acorn. The entire trip takes 20 seconds. So again, let's draw this path out. He went 4 meters to the east, 3 meters to the north. Okay, so we're going to change direction by 90 degrees here, east to north. So what distance did he travel? What was his displacement? What was the average speed? What is the average velocity? So here's our start and end point. Let's answer the distance first. Well, that's simple, right? We just add the distance traveled in whatever direction he travels. So 4 plus 3 gives us 7 meters. How about displacement? Well, we really are looking for the resultant, right, of this vector from our start to our finish point. Now, this forms a right triangle, so we could use Pythagorean theorem, right? 4 squared plus 3 squared would be equal to the square of the distance over here. And that value works out to be 5 meters, okay? Notice when we describe the displacement, we want to include a direction. So I'm just going to describe this direction as northeast. There's different ways to do that. We could have described this angle here, right? We'll get to that a little later in our study of motion, but for now, we'll just describe it as northeasterly, a combination of these two directions. And then average speed. Well, we know it took a total of 20 seconds. So we just simply have to divide our total distance by the time, and we get 0.35 meters per second. To find our average velocity, we're going to take our total displacement of 5 meters and divide it by the time, and we get a little bit different answer for average velocity. Okay? All right. So we've looked at this concept that all motion is relative. We know the difference between scalar and vector quantities. We can distinguish between distance and displacement and do the same thing in terms of the difference between speed and velocity. All right, so take a look in Google Classroom and you'll see the assignment that goes with this lesson. All right, thanks.